Okay, so we learned Q derivative and the Q integral. Now our goal is to find explicit definition of T and S instead of giving just a weight, a moment. Of T, S, P. We're going to find explicit formula for this. So recall how we define this. T is the operator whose kth moment is given by this formula. S, xk over. Okay. We will first find an explicit definition for S and T. Oh, I'm just write down this right away. It's just this. Because actually you can, if you are familiar with Q integral and derivative integral of x to the k, you can somehow see this dq cubed x. If you define this, you can check that this is true, right? Why? Let's see this together. What is the kth moment? We just substitute this over here. xk dq cubed x, right? But we know how to integrate this, right? It's just constant. So if you have kth power, here it will be k plus 1 q. But the integration variable q is q cubed. So here we have q cubed instead of q, right? And then we need to substitute x to the k plus 1, 1 and then minus q. So x to the 1 to k plus 1 minus q raised to k plus 1. This is just a q integral. I use the fact, right? I use this fact. All right? But you can see here, what is that? You cancel these two things and you get q to the 3k plus 1, right? What is this? 1 minus q to the k plus 1, as we wished, right? If we define this, that's the same thing. Okay? So we found an explicit formula for T. What is S? Similarly, and so first we need to define alpha so that alpha is a variable that satisfies this. Let's say alpha is like that. Then we define S. Yeah, actually, there is enough to define for this. We need explicit formula using an integral. Okay. Or if you want f of x, you can define like times q1 f of x x to the alpha dq cubed x. If you want, you can define s like that. Okay, but what is this? You can compute this as before. Here we add 1 to the exponent. The q is q cubed, and 1 minus q to the k plus alpha plus 1, right? Now you just compute this. Again, you can cancel this. 1 minus q to the q cubed, k plus alpha plus 1, 1 minus q, k plus alpha plus 1. But because we know that we define q to the alpha like this, you just it will just become like that, right? Is this as wished? All right, just a substitution alpha there, then you get that. So these two operators, T and S, are given really by just the Q integral, like this. Rather simple, not that hard. This and this. Okay, any question? Now what about P? Now it's more complicated, but in classical Q equals 1 case, classical case was already done, so people could guess and find this explicit formula for P orthogonal with respect to T is given by this formula. Pnx equals 1 minus q cubed, some constant, sub n d q cubed n I from 1 to n minus 1 one can prove that if you define this, then one can check if you plug in this there, this operator, you can show that these are, so it's a polynomial in x of degree, a monic polynomial in x of degree n, and you can check that this is 0 for different n and m. So it must be they must be the same. So of course this is not easy to come up. It's not easy to come up with this idea, but it was already done for Q equals 1 case by Roderick, like many years ago. So yeah, people were able to guess this and then found they were able to find this formula. Now what? We have explicit formulas for T, S, P, right? So what is that? Now we have the explicit formula for this. So this is the quantity that we want to compute. And this is just substitution, just Q integral. dq cubed n minus 1 x alpha dq cubed x. Right? All you need to do is to compute this integral. It's basically summation because Q integral is Q series. How can you compute this? It's product and applied to a derivative operator applied to this product, but we can use the product rule for the Q derivative. So if you do that, and then after a little bit of computation, this can be rewritten in this way. Summation using hypergeometric series. Times 2phi1, this basic hypergeometric series we learned. minus t squared. Yes, we have a formula for S. May look complicated, but still it's a formula. Summation involving just summation. Now we had this double star equation, if you remember. So let's go back to the double star equation. So we have a formula for this. And if you plug in the formula over here, and then finally we can take the Q equals 1 limit using that formula. Now we can take finally Q equals 1 limit in the equation double star. Then we get this. Equals minus 3. Now we don't have any Q here. Everything is just polynomial in T. Or two F1. 2 phi1 becomes 2 F1. Yes. Now what? What do you want to do? Finally, we can substituting the conjectured formula. So we have a conjectured formula for this. Then we get the left-hand side is like this. 1 minus W. Minus equals over here, this part, right hand side here. Now what? Everything is just a formula. Just all we need to do is to show that this is equal to this. Summation equals to another summation, right? This can be done. Nowadays, actually it turns out that this is in fact a known identity. It was already known. This is equal to this. Already known, so the theorem proved. But there is another way of doing this. Nowadays, an identity like this can be proved automatically, just by a computer. Nowadays, such a formula or equation, such an equation can be proved by computer. There is a computer package developed by there is actually a book. See, the title of the book is just A equals B. This is the title. Interesting title, right? By 3 people, Pat Kovcek, Wilf, Zeilberger. Zeilberger is the one who proved the ASM conjecture for the first time. He's a very strong mathematician in combinatorics, and he's also like very, very good at computer. They developed some computer programming package. So if you want to show some identity like this, you just use this package, and it will find some kind of okay, let me write this down. This algorithm. So here, both sides are functions in n, right? If you plug, you know, everything is n with t, you know. So both sides are functions of n. So how can I say? This algorithm finds a recurrence relation for satisfied by both sides. So if you say Fn left hand side or right hand side, then the program will show that F satisfies this 3 So the program will find this recurrence relation. That means both left-hand side and right-hand side, they satisfy the same recurrence relation. So if one checks that the equation true for n equals 1 and 2, then by this recurrence relation, they're true for all values of n. So it will be proved. So this is a very interesting book. It is the PDF is freely available online. I think if you just Google this, you will find this. So yeah, this kind of equation is now kind of trivial. So that's the proof of the the sketch of basically of the ASM conjecture. Proof of the ASM conjecture. Okay. All right. I guess this is it for this semester. Thank you very much for your attention. I really appreciate that you come to my class every week and submit your homework assignments every week, which was, I think, not very easy. It could be a challenging problems, but I really appreciate it. I didn't really expect you to work that hard. But yeah, thank you. That's it. Thank you.